As you already said, right? So I want to talk about upscale Python functions for high performance computing with Executorlib. And that's part of our greater effort to really go from the atomistic simulations to predict materials and ideally identify new sustainable materials by leveraging high performance computing. So just to give a brief introduction. So that we started with this challenge in my group to install new scientific software, right? In our community, a lot of software was openly distributed, but usually they were C++ or Fortran codes. So people really, while the code was available, they really struggled to install the code and then use new simulation codes. And so the first activity that we started with was really getting involved with the CondaForge community and really create a large number of packages for this specific field of materials informatics. By now, this is really like a group of 1,000 packages. And at this point, we are at the stage where when somebody else is now developing a new package in our community, usually it takes like 3 to 6 months, but then this package also becomes available on CondaForge. So we now covered really this process of installing new software in our field of materials informatics. In most of the cases can be done by CondaForge and just at least give you a first version of the software so you can play around with it, test it, and then see if this software is useful for your own research. But once your software is installed, that's only the first step, right? So the second step is then how do you use it, right? So like maybe different software packages have different units, different variable names. So that's what motivated us to enter this field of workflow development. And the first framework that we developed is this Pyron workflow framework for combining Python and then Iron, which was the previous name of our institute. And there we use Jupyter notebooks to really provide a structure for atomistic simulations, right? So you can see this here. You can look at the atomistic structure. We can then use Markdown to outline a bit what are the steps of the simulation we want to do. And then finally, we use this Python code to set up our calculation, submit it to the supercomputer, analyze the results, and ideally also the figure that we get in the end is the figure that we would use in a publication, right? So if now somebody comes to you after 5 years, maybe after 10 years, and says, how did you calculate this figure? We can always go back and show them the Jupyter notebook and say, look, these are exactly the steps, exactly the calculation that were into a specific figure. But the Pyron framework was very much focused just on atomistic simulations, so very domain specific and not so much generalized. Still, what we learned from this was that having everything integrated in this Python framework, so all our previous Fortran and C++ code, having Python wrappers around them, made it very easy to couple to machine learning frameworks. And first, these were simple neural networks or simpler frameworks, maybe Gaussian processes, but more recently also the large language model agents, right? Because these agents are very capable to write Python code. By having now Python interfaces for all our simulation codes, we can couple them to the large language model agents, to our simulation frameworks, and suddenly they can do material simulations from a text-based interface. Right, so previously, the Python interface was a barrier for certain users. By making it accessible to large language model agents, you can now even control the workflows with a human-based, language-based interface. I mentioned these examples just to highlight a bit how much we as material scientists really benefited from the workflow community and really how it helped us to then automate the discovery of novel materials. And then we moved one step further, and that was really for us this looking a bit beyond the scope of our own framework, the Pyron framework, and seeing other frameworks doing similar things. And just two I want to mention here. So one is the AIDA framework that's from Switzerland, also here in Europe. And the other one is the JobFlow framework, which is part of the materials project developed at Berkeley. And we noticed that all these frameworks somehow took a similar direction. All of them started by having the parsers very tightly integrated with their specific simulation framework. So the first part we agreed on in this kind of initiative was to say, okay, we want to make the parsers just pure Python functions and then share them between the different frameworks. So to be able to then not develop one parser for each framework, but to basically have one set of parsers that can be used in all the different frameworks. And then the second part of this collaboration was really to think about, okay, how can we now share these kind of workflows? And maybe in contrast to what is happening in other communities, for us, the workflows are really just commonly Python functions that are coupled together and Python objects transferred between these functions, right? In other communities, we commonly see files being transferred between different objects and maybe different executables from different programming languages. What we see in the materials informatics side, in particular on the atomistic simulation side, is that people use a lot of Python functions because it really allows us to very easily couple to machine learning models, which then accelerate our predictions. So when we have different Python functions, like I illustrate this here with this example, the next step after sharing these functions was also sharing the connections between them. And for this, we developed this kind of Python workflow definition as one interoperability framework. And you can read more about this in the publication below. But basically what it allows us is that we can write the workflow with one of these frameworks, export it to the Python workflow definition, then load it with one of the other frameworks, modify the workflow, and then execute it in another framework. And so it's really for sharing workflows within the different frameworks, or in the 3 frameworks listed here, really being able to collaborate more closely together and have a shared effort inside this community for materials informatics. And obviously the goal where we want to go is really to be able to not only share the workflow, that's the recipe part, so to say, but also share the data connected to this, where you have the full provenance exported from one framework and imported into another framework. But that's a story for another day, so that's not something we achieved so far. But what we noticed from this discussion was really that all our frameworks, we all use Python functions as the most fundamental building blocks. And then we develop these workflow frameworks and execute the Python functions inside them and coordinate them. And that made us wonder, can't we go the other way around, right? So can't we just start from the Python programming language and think about what do we have to extend from the Python programming language to make it a workflow language? And that's what I want to discuss on the following slides. And then I want to start very simple. So I have here a simple for loop where I just iterate over the numbers from 1 to 4 and then do the summation of 2 of these numbers and collect all these results in a list. And already the Python standard library provides the ProcessPoolExecutor interface as one way for asynchronous execution. So basically meaning we can run the summation of a pair of numbers in a separate process. And here the sum function is just one simple example. So this could be a much more expensive part. Let's think about this as a quantum mechanical calculation. Right, so what the standard library already allows you is to distribute this over different processes. Then you can check what is the status of the different processes, and then finally gather the results and bring everything together. So this is nice for Python parts, and it can be done with processes and also threads, but it's not really the kind of workflow functionality that we want. And in particular, it's missing the capability to upscale, right? So we really want to be able to run on large scales, even up to the exascale. So now if we look to the exascale side, here we learned a lot about the Flux framework, which is a hierarchical job scheduler, meaning in contrast to something like Slurm, where whenever you send like an srun request, it always goes via the central database. A hierarchical scheduler like Flux, you can get an allocation, a certain subset of the resources, and then within your allocation, you have a separate scheduler, which allows to do, again, subdivide these resources into different tasks and so on. So a very flexible approach. So in particular, when you have these very huge machines, allows you to address the complexity and achieve very efficient scheduling of your tasks. And what they also have, in addition to this hierarchical scheduling, is a very nice Python interface. And you can already see the similarities here. The important part is now, rather than sending Python functions to our scheduler, the scheduler is working with shell scripts. Here I just illustrate this with a bin true script, but that could be any kind of different shell script or a command to call an external executable. And the important part here is these are not running on one machine, but they are now distributed over a large number of computers. And basically you can use all the resources within your allocation. Right? And you can use the very same syntax to check when the results are done and get the response. Right? So what we see on the exascale side, they're using very similar kind of command structures to really then use Python to manage these kind of large allocations. And so the idea of Executorlib was just to bring these two concepts together. Right? So that's what I show here. The syntax is very much the same as the executor from the standard library. But rather than starting local processes on your computer, what the Flux jobs executor now is doing is using the Flux scheduler to get tasks distributed over all the different resources in your allocation. Right, so I try to indicate this here with the small dashed lines, right? So these are no longer processes running on one compute node, but these could be processes scattered over the whole computing allocation. You can use the same functionality. We can use the done function to see how our future objects computed. And then also the results function to validate, okay, we get the final results. Right, so this is very intuitive for somebody who is already familiar with the Python standard library and has some experience in Python programming. There's no overhead in switching from writing a Python script to writing a Python workflow with Executorlib. Right, so it's really exactly the same syntax. It's just the import where you get your executor from. It's the only thing you have to change. You only have to import it from Executorlib rather than from the concurrent futures standard library. All right, so in addition to the submit function, it also implements the map function to really fully reproduce the interface of the executor class. So to bring this to a bit more abstract perspective, here illustrate this in a schematic way. There are different executors that are now implemented in Executorlib to really follow the scientist over the whole journey, starting with the development on their local computer. There we use the single node executor and use socket for the communication. Then maybe running their workflow on the first local supercomputer, where they most likely will use Slurm and maybe use file-based communication because they submit the calculation from the head node one by one, and every calculation gets its own allocation. Then we also have this Slurm job executor, where we ask for a larger allocation and then basically use srun to submit the individual tasks, and then again use the sockets for the more efficient communication. And finally, we have the interface to Flux, which allows us to do the very same on the exascale within a hierarchical manner to really schedule thousands of compute nodes in one framework. And really, the advantage here is that as a user, now the compute cluster really feels like one big computer. Right? So there's no difference of running a ProcessPoolExecutor on my single computer with a limited number of the processes, or on one of these exascale machines with thousands of processes. Right? So it's really just the core functionality or the focus for us designing Executorlib was to simplify the process that the scientist goes through when they upscale their workflow. Right? So starting from a local computer, then their local HPC, maybe at a university, and then upscaling it to the latest exascale computers. Always using the same syntax, and the only thing they have to change is basically the kind of executor that they import, but all the commands that this executor supports all remain the same. And once we had this working, we noticed, okay, there are more features that we want. Right? So one of the features is the ability to run MPI parallel code. So what we saw with our users was that there's always a transition. First, scientists write a serial program, and then when they want to upscale it, run it maybe on a larger HPC, they have to translate it to use an MPI parallel version, maybe using MPI for Pi. With Executorlib, it's now possible to only do the MPI parallel part for the individual functions where you need the compute resources, while keeping the rest of your program in a serial manner. Right? So we can submit functions, and by adding this additional attribute here of the resource dictionary and assigning a certain number of cores to the specific function call, this function is then executed MPI parallel, so therefore using multiple cores. But the rest of the program, right, our definition from the executor, introducing the single nodes, the definition of the function, and the whole logic of our workflow, so to say, all this remains a serial process. Therefore, making it much easier for our scientists to really write these single functions where they benefit the most from the parallelization, while keeping the rest of the protocol all in a serial form, and therefore accelerating the process of upscaling their workflows. This can be done with MPI parallel task. If we now switch to something like the Flux job executor, so if you have a full queuing system behind this, we can also assign other computing resources. Right? So we can assign the number of CPU cores, the number of threads, the number of GPUs, assign a specific working directory. Depending on which resources you want to be available for your specific function, all this can be assigned using your job scheduler and then the function is executed in an environment where it has access to this specific resources. Right, so this really drastically accelerates the process of developing, and in particular the upscaling part, because we only parallelize the part where we really benefit from the parallelization, and the rest of our protocol can remain serial, because it would just be an overhead to rewrite this and make it into a parallel Python script. The same becomes true when we have this kind of caching functionality, when we now think about the individual functions that we submit, right? So all these are simple examples, just like an addition, but think about this as like an expensive quantum mechanical calculation. In that case, you don't want to, during your prototyping, you don't want to always repeat this kind of calculation when you run your workflow, you do the development of your workflow. So you want to have the ability to cache the results, and that's also possible with Executorlib. It's caching the results into HDF5 files, and then it can aggregate the data of these submitted functions in terms of like a pandas data frame. So it's really like a MapReduce kind of an approach. You submit a lot of calculations, you get this pandas data frame, where you always see the input arguments that were submitted for the specific functions and the corresponding output, and even the runtime to debug a bit how efficient your computations are. Right? Obviously, when we use the cache, we rely on the file system. So this is not going to be the most efficient part, but it's very effective at the point where we develop our workflow, because it allows us to cache the results and iteratively extend our workflow, and not being forced to first write the full workflow before we can start with the testing. So we see this, the focus here was really to what are the kind of tools the scientist needs to be able to accelerate their development process, and caching and storing intermediate result and being able to run a workflow up starting from a fixed point, run everything below this again. That was really like a key feature that our users asked for. And then the final part is really this question of, okay, how do we represent dependencies with these kind of executors? Right, so and that's what I show here. On the first iteration, the future object, the future object is just the value 0, but then starting from the second iteration, the future object is used as an input, or the future object is used as an input for our addition. And then in the second iteration, the future object comes from the previous iteration, right? You see, it's always linking to the previous part. We can even visualize this. So that's what I show here, right? So we see the first two numbers are added, and then the result of the first two numbers goes into the next addition, and so on. Really just showing these dependencies. So we represent the dependencies and any kind of directed acyclic graph, so any kind of DAG, by using the future object as an input for the next calculation. And there's no need for us to say, okay, wait here until the result is available. The executor is handling all the dependence of the different future objects. And the same graph can even be exported to this Python workflow definition that I introduced in the beginning, right? So the graph that is created by having these future objects depending on each other can also be exported, and then can also be used with all the different other workflow frameworks that I introduced previously. All right, so this really allows us now to construct more complex workflows. And so I want to now switch gears a little bit and show a few of the workflows that we're using this framework for, and the kind of applications that we do. And one of the main topics on our side is really this generation of machine-learned interatomic potentials. So we start by having quantum mechanical calculations of rather small structures. And then based on a large set of small quantum mechanical calculations, we train an approximative model, and this can be classical models with analytical forms, or neural network-based approaches, or more modern generations of machine learning potentials. And we basically train them on the quantum mechanical data. We validate first with material properties, which are also accessible from quantum mechanical calculations in some kind of active learning cycle. And then ultimately, we use these machine-learned interatomic potentials to then calculate properties which are not accessible from quantum mechanical calculations, like in this case here, the phase diagrams. And that's what I show here. On the right side, we show a phase diagram which is derived based on experimental data and available in a commercial database, the CALPHA database, which is frequently used in our community. And on the left side, I show for the same material system, the phase diagram calculated from our quantum mechanical calculations. Right? So the only fitting parameter that goes into the result here on the left side is the interaction of the electrons. There's nothing material specific in there. And all the rest is just quantum mechanics and thermodynamics combined. And you see there's still quantitative differences, but qualitative, we already have a very good agreement. And we also have a strategy to move forward to really address the quantitative disagreements. So the goal there is really to be able to calculate these phase diagrams for any kind of material compositions and any kind of material just from these quantum mechanical calculations, to be able to make much more precise predictions what kind of material properties we would expect. But then to develop these potentials, that's where we need the compute power. Right? So that was part of the exascale computing project, where in very simple terms, we can think about it as a three-step process. The first process is calculating our quantum mechanical calculations, then the fitting of our machine learning model, or in simple terms, just any kind of coarse graining model, and then finally some validation or active learning processes. And previously, this was always like a step-by-step process. In the worst case, even you have one expert for the quantum mechanical calculation, one expert to define the coarse-grained model, and one expert doing the validation part. So you can easily see how this process of developing one of these models goes easily from a few days to even weeks or months until one of these projects is done. So the question in the exascale project was, how can we bring this time down, and maybe can we construct a machine learning potential in the order of days or maybe even hours? And our approach for this was move away from the step-by-step workflow more to something like a streaming workflow. Meaning we start the first quantum mechanical calculations. We maybe submit 1,000 of these calculations. But as soon as the first 100 of those are finished, we use the first set of hundreds to fit the first machine learning potential. We use it to do maybe some kind of hyperparameter study, and then use the first machine learning potential to do the first active learning, way before the full set of calculations is done. Right? So it's by breaking it down into smaller chunks, we are able to always keep our quantum mechanical calculation, which are the computationally most expensive part, always keep those running, and very maximize, therefore, the resource utilization of the compute resources we have available. Here's just a run that we did on the Frontier machine with 256 nodes, where you can see the number of completed tasks on the y-axis and then the runtime on the x-axis. And we see, okay, in the first 10 minutes, nothing is completed. And then we see first the quantum mechanical calculations are completed. Then we have the calculation of our descriptors for constructing these machine learning models. Then there's a step when we do the first fit, and then the validation. And like this, we're always building up a better and better model. And that's what we see here in the second graph. So here's our uncertainty for our properties, or the RMSE in our prediction, and then over the compute time. And we see after a little more than 100 minutes, for this example case, it was converged, so the program stopped. Right? So with this, by doing this kind of automation, we brought this process from previously more in the order of weeks or even months down to something that can be done in the order of minutes, because all the tasks are coordinated and we're really able to leverage the resources available on these exascale machines. So what was the underlying challenge? Right? So if we break it down to the most simple part, is this runtime dependent scheduling. Right? Let's say I submit these 5 tasks that I show here, and I want the first 2 of these tasks that finished to go into 2.1. But at the point when I do the submission, I cannot approximate which of my 5 tasks will finish first. Right? Let's say this could be 1 and 4, and then the second ones could be 2 and 5, and maybe the last one is task 3. How do I write this kind of runtime dependent workflow in a very simple form in the Python programming language? Right? So how do I transfer these dependencies to a Python code so that the workflow manager can understand this. And that's what we worked on with Executorlib, right? So for these first set of tasks, we just create a list of future objects. And then we implemented a batched function, which is exactly the same as the batched function you know from the iter tools in the Python standard library, which is just grouping them together. But rather than acting on the future objects, this batch function returns future object itself, but the actual mapping, which tasks are represented in this future object, only happens at runtime, right? So we think this is a very elegant way to move this complex problem of the scheduling to a nice Python syntax. So it's very accessible for our scientists to really benefit from these advantages that the latest generation of exascale computers bring us, right? So it's, again, this is the same philosophy that we also have with the Executorlib in general, to take the interfaces that people are already familiar with from the Python standard library and apply them to the scaling or to the running Python functions in the HPC context to really make this transition from running on your local computer to running on an HPC as seamless as possible. Another feature that we realized that we need is this ability to preload large data sets, right? So in the case of us fitting the machine learning potentials, we always want a huge data set where we do the fitting on already available in the process. So for this, we now define this kind of initialization function, which populates a dictionary. In this simple example, again, the data that we transfer are just integers, but think about this as maybe a large data set that you load. When you then submit a function to this executor, and here we submit this function which takes 3 inputs, and we only provide 2, right? So we provide I is equal to 2 and j is equal to 5. So we have no parameter for the k. In this case, the executor automatically has access to what is populated from the dictionary from the initialization function, sees that the k is defined here, and then loads the data from the memory of the executing process. Right? With this, we can keep parameters located on the process that's doing the execution, and we don't have to reload big data sets or other elements for every iteration again. Again, the focus here is how can we accelerate the process and make the data loading as efficient as possible while still providing our users with a very simple Python interface, which is as close as possible to the standard library and the functionality that's available there. The same also works with the Flux executor, where we even have the option to assign how many resources are available for these individual workers. Right, so again, this reduces the overhead of the communication of always sending the data set back and forth. And then the final part here is really this kind of hierarchical scheduling that Executorlib is known for, that Flux is known for. This can also be represented in Executorlib by just nesting the executor inside the Python function. So here I submit this Python function, and by adding this additional flag of nesting the executor, it starts another Flux instance in the resources that are given to this Python function, and then can use another instance of the executor to access the resources inside this nested executor. Right? So really being able to represent the full hierarchy that is used for this kind of complex workflows on the large-scale computing, while still maintaining a rather simple structure how we build the corresponding workflows on the Python side. With this, I come to the concluding part. All these developments are available as open source, so you can find them on GitHub, Pyron/Executorlib. We learned from our previous projects, so we do a lot of testing for Executorlib. In particular, we also test with Slurm and Flux as part of our continuous integration. That's something that took a lot of time, but helps us to identify challenges early. We are also big fans of the Jupyter Notebooks. We use the Jupyter Notebooks for documentation, for testing, and for demonstration. The important part, these are always the same Jupyter Notebooks. So what you see on our documentation is also used as part of our integration tests. So you're always sure that this code is also working, what you read on the documentation. And when you launch this MyBinder service, you can even have like a Docker instance in your browser where you can access these parts and use them for demonstration and test exactly the same notebooks. So that was really for us a the thought process, how can we construct a way that we always do this testing and documentation and demonstrations all from the same set of examples. And we do this now with the Jupyter notebooks. Finally, it's published in the Journal of Open Source Software Science. And as it's a new project, we're always happy if people give us a GitHub star to really build some momentum and show this project to more people. With this, I come to my conclusion. I hope I was able to show you a bit the challenges that we have in terms of these streaming workflows in material science and these runtime-based dependencies, how we address this with a framework like Executorlib, where we in particular focus on this process of starting the development on our local computers, upscaling then to an HPC, maybe at a university, and then finally extending this up to the exascale. And finally, how we go beyond just submitting Python functions, but also representing the dependencies and therefore having really the full workflow represented in our framework. And with this, I'd like to thank you for your attention.